I was asked if I would give this talk. I said, thank you very much. I'd be delighted to. And I thought, well, what can I talk about? And I thought, I know what I'll talk about. I'll talk about a paper that we wrote, that Professor Michael Bates and I wrote with some colleagues from the University of Bielefeld last year. It was published just this summer and was a year in the making. And of course, I forgot to read it before deciding I would make this the topic of my talk. And that was a major mistake because there's an enormous amount of material in it. And I had forgotten how much material there is. So nonetheless, I'm going to make an attempt to see if I can get through and cover the material in this paper as best I can. So this is work by myself and Michael Bates, Josephine Albert, Xiaoshui Shuan, Helga Ritter, and Werner Schneider in the University of Bielefeld. So thanks to them for all of their contributions. So this is their work as much as it is the work that I'm describing that I did. So I want to talk about everyday activities because that really is the focus of ease. And the idea that we want to build robots, cognitive robots, which are capable of working in everyday environments, doing everyday activities. And I want to start by differentiating between different types of activities, the simple, the complex, the easy, and the difficult. We, people, humans, perform activities routinely every day, and we think they're easy, but it turns out that sometimes they're not quite as easy as you would imagine. And so we thought we'd try and decouple these different elements of how you can characterize different activities and tasks. So I want to talk about the difference between simple tasks. So a simple task would be, for example, stacking plates. Why is it simple? It's simple because there are strong constraints on what you can do with the plates. You can pick them up and you can put them down on top of each other. So there aren't very many steps, and the degrees of freedom in each step is pretty limited. Complex tasks then are quite different. So in this particular case, you've got, for example, filling a dishwasher. Where you put it matters. In order to do effective washing, you have to make sure that the surface is facing the stream of water, and you want to be efficient, so you need to have a full load. So there's a lot of variables and a lot of steps involved, so many degrees of freedom. So these are two different ways of characterizing tasks or activities. So in this case, complexity is an attribute of the task or the activity. But when we think about whether activities are easy or difficult, well, it's a slightly different matter. In this case, it's going to be dependent on the familiarity of the cognitive agent with the task. And it becomes difficult if that agent hasn't been exposed to that task very often. And typically then they'll struggle with it with effort which is beyond the intrinsic complexity of the activity. So in this case, we understand the difficulty to be what we might call task transparency. That is, how evident it is to the cognitive agent whether or not or how to approach that task or that activity. So this is how I'm going to characterize everyday tasks as simple and complex or easy or difficult. And then I want to explain to you how we can go about tackling each of these different activities and what type of mechanisms we need. Because what we learn from cognitive science is that we need different mechanisms in our cognitive architecture in order to accomplish tasks in a habitual way. These would be the easy ones, or other tasks, these would be the difficult ones, and they require more deliberation. So after a while, though, an agent, while they may initially have to deliberate over a simple task, they can then find it easy subsequently after executing it a number of times. And it becomes routine for that agent in that case. The same is actually true of complex tasks. Even though you require deliberation in order to accomplish it, with some work, it can become easier with repeated routine execution. And the question, of course, is, well, how are we going to model this computationally so that we can build cognitive robots which can accomplish both the easy and the difficult, the simple and the complex, and also how they can learn to make your difficult tasks easier by routine execution. And that's where we're going this afternoon. It's also worth remembering that things go wrong. And so if something unexpected happens, then what was originally an easy task can sometimes become difficult, and you may require deliberation in order to complete it. Okay, so CROM is a cognitive architecture. CROM stands for the Cognitive Robot Abstract Machine, and it was developed explicitly and specifically to allow robots to carry out, in the first instance, easy, simple, and complex tasks. And what I want to do in the first half of this talk is explain how it does that, and then explain how in the next generation of CROM, in the next phase, the current phase of ease, how it should be able to tackle the difficult. And that's where we will be going. How does it do this? It does this by taking what we call underdetermined action descriptions and then using a generalized action plan for, in the particular tasks that we're interested in, first of all, is fetching and placing objects. But it's not restricted. You can do other types of manipulation as well. So just to give you a flavor for it, and in case you haven't seen it, I want to show you this video. Okay, so that's extremely impressive. And the question then is, how do we do that? How does CROM do that? It's addressing 5 key challenges in carrying out this table setting and tidying up task. The first thing is that the request to do this is underdetermined. That is, you say, fetch me the cup or fetch me the bowl. And secondly, you need to be able to do these actions using context. You also need to be able to use knowledge, as Gaia said. And then you also need to be able to reason about the task at the motion level. It's not just reasoning about the fact that there is a cup and you have to grasp it, but you have to know how to manipulate it. So you need to think about your manipulation as well. And then finally, the robot agent should be able to answer questions about what it's doing and why it's doing it, and how it could improve it. So these are the challenges that face us in carrying out everyday activities. And so this is the key chief characteristic of a cognitive agent, the ability to achieve goals by acting in a world that's uncertain, it's underspecified, it changes, and possibly there are other cognitive agents involved as well. And the problem is that to achieve these, we need a very, very complex software system. And that software system is called a cognitive architecture. It's the framework which allows the system to construct models of the way the world works, and then to guide your actions prospectively. That is, to anticipate the outcome of the action before you undertake it, and then to update your models dynamically as things in the world change. So let me give you a very brief introduction to the world of cognitive architectures. As I said, it's a framework in which we integrate these core cognitive abilities. I've listed 8 of them here: perception, attention, action, selection. You need memory, you need learning, reasoning, you need meta-reasoning, or sometimes called metacognition. And you need prospection, that is the ability to predict the future and anticipate the future. And you need to do all of this in a context-sensitive manner, selecting your actions and controlling your actions while you're achieving your goals. The cognitive architecture is not just a picture of modules. You also have to commit to the interaction between those and the algorithmic and representational details in each module. So it's a cognitive architecture is equivalently a software architecture, which reveals exactly how your cognitive system is going to be implemented. And there are 3 paradigms of cognitive science: the cognitivist, hybrid, and the emergent. And the word cognitive architecture, the term cognitive architecture, was invented with Alan Newell, who was a researcher in the cognitivist paradigm of cognitive science. And it's subsequently been adapted for use with hybrid systems and emergent systems. So what's a cognitivist cognitive architecture? For Alan Newell, it was a model of cognition which covered all of the issues from every aspect, from psychology, from neuroscience, from computer science. So it really was a grand unified theory of cognition. And it's a major research goal even today. One of the issues of the aspects of these cognitive architectures is they are generic in the sense that they are not specific to any one given task. In order to make them specific to a task, you have to add knowledge. So your architecture plus your knowledge then gives you your overall cognitive model. On the other side, the emergent cognitive architectures, they focus on development. So initially, they're not able to do a great deal, but over a period of time, as they experience the world, they develop that capacity for cognition into a capability for cognition. And they focus less on knowledge and more on skills that are adaptive and that can anticipate the outcome of executing those skills. They are also focused on the morphology of the body in which the cognitive architecture is implemented. And today the trend is for to combine both in what are called hybrid systems. And for the most part, this means that they're using both symbolic and sub-symbolic representations and computational processes. There are many cognitive architectures, and there are many surveys of cognitive architectures, but the one I want to draw your attention to is one by Yulia Kotsaruba and John Tsotsis in York University in Canada. And they surveyed 84 cognitive architectures. And they call the cognitivist cognitive architectures symbolic cognitive architectures because they derive from the symbol system hypothesis of Alan Newell and Herb Simon. And here we have the 84 of them. And you can see just from this diagram, clearly how they're divided. Most of them are hybrid. Some are symbolic and some are emergent. And I just want to draw your attention to a few of them. The first one would have to be SOAR, which was Alan Newell's cognitive architecture, the one he started off with. It was his candidate for a unified theory of cognition, and it's still being developed strongly, and it's being developed by John Laird. It's an interesting cognitive architecture because it's got pretty much everything that you need and would expect, unsurprisingly, because it's trying to answer all of the questions about cognition. I'll just draw your attention to a couple of the different aspects of it because we're going to meet them again shortly. So we've got semantic memory, we've got episodic memory, which is autobiographical memory of the experiences of the agent. procedural memory. It's how it operates and how its skills you can learn both episodically and semantically. Chunking is a term which we use to describe learning new rules, and it's got reinforcement learning today. And all of these are new additions over the past 6 or 7 years. The symbolic working memory, which I'm going to mention later on when I talk about the situation model framework, turns out to be extremely important for the effective, efficient working of the system. It's got a perceptual short-term memory and a long-term visual memory as well. And also, this box here, this mental imagery, is very important because it's the mechanism by which you can anticipate the outcome of performing an action and the future state of the system. It's got perception, obviously, and then it's also got action. If you want to have a really nice introduction to Laird, I would recommend watching this short video by John Laird talking about and introducing the SOAR cognitive architecture. I'm not going to do that now because we started late and I'm a little short in time. So I'll just flag a few more archetypal cognitive architectures. ACT-R, which is based on John Anderson's unified theory of cognition, still being developed and the subject of research. Clarion is Ron Sun's cognitive architecture. It's remarkable for the manner in which it combines symbolic and sub-symbolic processing together. And it was originally developed and still a model of human cognition rather than being developed for a robot system. In the emergent side, we've got brain-based devices. This is Jeff Kritschmar's cognitive architecture, and he takes a different approach to things. He's interested in emulating how the brain would actually accomplish a task. And this has given rise to a new domain in robotics called neurorobotics. So it's focusing on neuromimetic, or mimicking the operation or the structure of the brain in a fairly faithful manner. Isaac is one of my favorite. It was developed by Kaz Kawamura. I like it and I use it when I teach a lot because, as you can see here, it's got all of the aspects that you'd expect in a cognitive architecture, all the different types of memory. It's got short-term memory and working memory as well. It's got attention. And then it's got, and this is what we didn't see in the other one so far, it's got an affect agent. That is to say, it's got an emotional response, and the emotion is modulating your decision-making. And then it forms intentions and the emotional center of the system, which is important for decision making, is also impacting on the decisions that the cognitive architecture makes. So it was originally developed for a humanoid robot system. And if you want to know more of them, and in the last 5 minutes, I can hardly cover the last 30 years of cognitive architecture research, but there are some really, really nice videos, short 15-minute videos given by the people who developed these cognitive architectures themselves. So we've got Kaz Kawamura here, we've got John Laird, we've got Ron Sun, and we've got Sean Kugley, who was standing in for Stan Franklin, who developed the LIDA cognitive architecture, and we've got Jeff Kritschmar with the BBD one. So definitely worth looking at, and you'll find out a lot more than I can tell you in the last 5 minutes about these terrific cognitive architectures. I want to spend the time that's left talking about the CRAM cognitive architecture. And this was introduced by Michael Bates, 11 years ago. But of course, even then, it had a long history prior to that. And it is still being developed today actively, as I'll show you. It's a hybrid cognitive architecture, and it was designed explicitly to address robot manipulation in everyday tasks. And so the challenges of everyday activities, as I've mentioned, are the fact that they're underdetermined. We have to use context. We need to use knowledge and experience. And we have to be able to reason at the motion level about our manipulation. We need to know how to interact with our objects that we're manipulating and answer questions about why we're doing it and what we're doing it and what we expect to happen when we do it. So the key elements then of the CRAM approach are these idea of an underdetermined action description. This is very important. The idea that when we ask someone to do something, we don't tell them how to do it. We just say, please do it. The generalized action plan is one of the mechanisms by which we bring that about. And what we're trying to develop is a motion plan, because that's what you execute in order to carry out an activity or an action or a task. And we transform from the number 2, the generalized action plan, to the motion plan using a process called contextualization. And I'm going to explain that in some detail in just a moment. And that uses a concept called a generative model, which is a way of saying what are the outcome of carrying out a certain motion. So if I carry out a certain motion, what will be the impact of that in the world? So the design of CRAM was based on the following principles. We wanted to be able to say, fetch a spoon or fetch an object, put it on the table. So this is a vaguely stated high-level goal, and somehow we've got to create a sequence of low-level motions which actually accomplish and carry out that and accomplish the goal as you wanted. So this mapping is accomplished using what I said was the generative model. So it's a symbolic and sub-symbolic knowledge representation, which allows you to map from the high-level underdetermined goal specification to the specific actions that will be successful in carrying out that action. So CRAM then focuses on these abstract specifications. And this means that knowledge is missing. So the question is, where do I get the knowledge? Well, you get it at runtime. And you get it at runtime by, the word I'm using here is resolving, because you resolve what's unknown. And there are a number of possible ways that you can resolve it. You might have prior knowledge, which could be stored in your plan. There's the current world state, because you have a perceptual system. But also you might have knowledge that you can reason about. So the control program that CRAM uses is what's called a generalized action plan. And it is we've got one of these for every type of action description. So we've got an action plan, generalized action plan for fetching, for placing, for pouring, for cutting. And that plan can be then executed. You can also reason about it and then transform it. And that allows you to improve your performance of carrying out these plans in the future. So we map from a generalized action plan to a motion plan, and the process that we use is called contextualization. It's a 3-step process, and I'll walk you through it shortly. In terms of, you'll hear me talk about what we've already said, underdetermined action descriptions. We perform these. That's the same thing as saying we execute a generalized action plan. And that's the same thing as saying we resolve a high-level action designator. So an action designator is no more than a placeholder for the information, the knowledge that you need in order to carry out that task or that activity successfully. So to do this, EASE and CRAM has borrowed from some work by Randall Flanagan, and where we map from a high-level plan to this lower level. So this is the motion phases in a CRAM plan. So this is what we want to map our vague, underdetermined action description into this reaching and grasping and gripping and lifting. The key thing here is that these are fine-grained elemental motions that you carry out, and each one, and this is the key thing, has a parameter associated with it. Which object are you going to reach for? What arm are you going to use? What pose are you going to place your arm at in order to grasp it? And so on. So for each motion, we've got a set of parameters, and each of these parameters have to have values. It's the values that make a motion specific and useful for carrying out manipulation. So CRAM, the cognitive architecture, then has 5 different core elements. And I'll walk you through them just very, very briefly. It's got the CRAM plan language executive, we'll just call it the plan executive for short. And it allows you to write your control programs using the CRAM plan language, or CPL, which is actually an extension of Lisp. And one of the key things about this language is it represents everything in the plan as a first-class object, and using a first-order logic. Now, the implication of that means that a plan itself can be reasoned about. So the CRAM cognitive architecture can reason about the plans that it uses to carry out these activities. And the point of that is that you can improve your plans through reasoning. That's the key thing with this. So the plan specifies how you should respond to your sensory events, your belief states, and also things fail in robotics very, very often. And all of this then can be inspected and reasoned about in the cognitive architecture. Each plan comprises this idea, this concept of a plan designator. So we've got 4 different types. We've got designators for high-level actions. We've got designators for objects, for locations and motions. Now, remember that a designator is really just a way of saying, here's something I need to know, but I don't know yet. And you need to find out that information at runtime when you are running your plan. We say we are resolving the designator. So the plan executive then interprets these generalized action plans, and here's an example of what it would look like in Lisp. We have an action. These are action designators of type fetching, an action of type placing. And then I can extend that. There's an action, there's an object designator. I want to fetch and place an object. And there's a location. Where are you going to put it? You're going to put it on something. What's that something? That something is a table. So you can see here how these, just going back up very quickly, these 4 type of designators are sufficient in order to completely configure a plan. And to carry it out, then we have to resolve these designators. How do we resolve them? We resolve them with a priori knowledge, which could be in the plan itself, over here in the plan executive. And this is how CRAM accomplishes simple tasks. Or another way of putting it, how it accomplishes habitual processing. In other words, it has sufficient knowledge already stored in its plan so that it can just acquire the required information or knowledge and then execute the plan successfully. On the other hand, the task might be complex, and therefore you need to engage in some deliberation. And that requires you to use the NoRob2 knowledge base. And it will provide the information necessary to complete to resolve the designators, and therefore so that you can carry out your plan. You'll also make use of information which is being required by the perception executive from Robo Sherlock. So you need to know what's going on in the world, as well as having sufficient knowledge in order to complete the resolution of your generalized action plan into your low-level motion plan. So NoRob, very, very briefly then, is a knowledge representation and reasoning executive. It is an encapsulation of a generative model. Effectively, it is the subsystem which allows you to identify what the motions, if you carry them out, what impact they would have on the world, what the effect would be. And then you choose the ones that would yield success. In other words, you choose the motion parameter values that give you the result that you want. And that's what we call a generative model. This is the joint distribution of the motion parameter values and their associated effects. So different values for different motion parameters will give you different outcomes. And then NoRob is effectively the subsystem which allows you to find out what those outcomes will be, and you'll choose the one that gives you the right outcome. So that's here. So you'll choose the one that gives you the outcome that you want. So it's a knowledge representation system. It's got a reasoning framework. It's implemented in Prolog, and it uses first order internal logic. But an interesting thing about NoRob is that it can also represent things that are going on in the world, perceptual information also, as in a way which is accessible to reason. So this allows CRAM to represent its common sense, background, intuitive physics knowledge in order to figure out how to accomplish a task, how to grasp an object, how it has to be held while you're moving it. If it's got liquid in it, it has to be held upright, you can't tilt it, and where you'd go to find that object. So all of the things that are missing from your underdetermined task request. And as I said, the knowledge can be a priori and stored in the plan. You can derive it from experience. You can also derive it by simulating the execution of your actions using a virtual reality physics engine. And so the 5 core elements then in NoRob are embedded then in a reasoning shell. And this is exposing everything to the world as a logic-based language layer. And this means that you can query it. So the 5 core aspects are the ontology and axiomatizations that basically organizes knowledge about the world, the robot configuration, where things are, what things look like. And then the axioms, they tell you what role the objects can play. And so together, these things allow you to understand and capture all of the information and knowledge that you need in order to resolve your high-level action designator, that is to carry out and perform your generalized action plan. We've got a generalized symbolic knowledge base. So it is allows you to extract general knowledge from these concepts called nemes, which you learned about yesterday afternoon. So what's a neme? A neme is a narrative-enabled episodic memory. It's one of the main features of the CRAM cognitive architecture because it records the robot's experiences, its perceptions, its poses, its controls, all of the low-level data that is involved in carrying out actions, together with the symbolic narrative of what it was doing while it was carrying those actions out. So, and these together give you this hybrid representation. You have your subsymbolic sensory motor data and a symbolic narrative explanation. And that's one of the main strengths and the key features of the CRAM cognitive architecture, this ability to have your symbolic and your subsymbolic representations wrapped up together. So a neme then is an episodic autobiographical memory with your experience and a narrative explaining what you were doing while you were carrying that action out. And it provides then the basis for the answers to the queries, the fifth challenge, if you remember, of carrying out everyday activities. So it allows you to answer questions about what actions you were performing, how they were performed, and what the robot believed when it was performing them. One of the key aspects of any modern cognitive architecture is that it has to be able to anticipate the outcome of actions. And CRAM accomplishes this with an inner world knowledge base, or a digital twin. So it performs geometric reasoning using a virtual reality and physics engine. And so you simulate the outcome of your candidate actions and then establish whether or not they are feasible, and then choose the one that gives you the best outcome. It also provides you with symbolic names for each of these, and you can infer background knowledge about, for example, where an object is stored. Because if you know you're looking for a cup, you know it's going to be in a cupboard. If you know you're looking for milk, you know it's going to be in a refrigerator. You know because it's part of your knowledge base. And so that inner world serves then two roles. It allows you to represent what you believe about the state of the world, and it gives you a mechanism for determining the outcome of your candidate actions. So these two types of knowledge are stored in this inner world, your current beliefs and your projected simulation of future states based on the robot's actions in the world. So this allows CRAM to determine whether or not carrying out its selected motion plan would in fact give it the result that was necessary. And it also provides a way of a learning mechanism, because you can run these simulations offline when you're not acting in the world. And that allows you to generate memes, and you can store your memes, which are based on simulation rather than based on memes which were acquired during the actual execution of a task. Finally, we have the virtual knowledge base, and it's the mechanism by which information which comes from your perceptual apparatus is made accessible to the reasoning system. And so therefore you can reason about what's actually happening in the world through your perceptual apparatus. And that makes your perceptual system accessible to symbolic manipulation. It also provides a view of the plan executive. Now, this turns out to be important if you want to reason about your plans. So you can have a view of your plan interpreter, and you can improve it. And this gives rise to the capability for doing metacognition. All of this is wrapped up in your logic-based language interface, which means that you can view NOROB effectively as a purely symbolic knowledge base, despite the fact that it has access to all of this sub-symbolic information in its memes and through these computational predicates, which it gets from its perceptual system. Right? So that's very, very neat. So being able to give this logic-based language interface to the rest of the system. And that means that your plan executive can ask questions. It can query NOROB. It can say, could you please tell me the values of my parameter value, the values of my motion parameters, which would allow me to accomplish the following task. And it also facilitates metacognition. CRAM's also got an action executive, which carries out the low-level motion plans, and it's got a perceptual system which acquires information about the world in real time, which we saw in the video by Guyan. And then just to finish off, cognition is your ability to improve action plans, generalizing them or specializing them using themes. If you think about it, the space of possible motion parameter values is absolutely enormous. And if you had to search through all of that, your problem would become intractable. So instead, in CRAM, we have this concept of a manifold, which is a subspace of all of the possible values that might yield a successful solution. So it's a way of restricting your search for the motion parameter values that will accomplish your plan successfully. So there's how it's going to work. I'm going to walk you through now the execution of a generalized action plan. So I'm going to map from a generalized action plan to a motion plan. So here's how it happens. First of all, you have an action plan for the type of action you want to carry out, and it could be fetch, it could be place, it could be pour, cut. So let's say it's a fetch the cup and place it on the table. So you identify that generalized action plan, you select it because from the right category, and the next thing you do then is you need to contextualize it. So that contextualization happens in 3 steps. So remember, I'm mapping from my generalized action plan to my motion plan. The first thing is you instantiate the generalized action plan by inserting the arguments that you need to carry that out. So for example, which object do you want to fetch? And these are represented, as I said, with designators. And then you extend that by adding the parameters which you need for your motion plan. So which object would it be? Which arm? What grasp pose would you like? How would you like to have the object when you lift it, for example? And all of these parameters here have parameter values associated with them. And depending on the parameter value, your motion will be successful or not, or your action will be successful or not. So you need to find out, well, what are the parameter values? How do you do that? You create a query for NoRob. And then you send that query to NoRob, and NoRob uses its reasoning mechanism and all its experience and all of its both the sub-symbolic and the symbolic knowledge. In particular, what it's doing is it's sampling this generative model. It's finding out what are the values of the parameter, the motion parameters, which will make this successful. And it can also use prospection. So once it has identified potential parameter values, it can execute them in its inner world and simulate their execution and then see, well, did it work? And when it finds one that works, it then sends that back to the plan executive, and the plan executive then sends it to Giscard for execution. So that's the way that CRAM operates. By performing a generalized action plan, resolving your action designator, by querying NoRob, looking for the values of the motion parameters, which will give rise to a successful motion and therefore a successful action. So that's how it works. So all of these, of course, are the simple tasks. That is to say, they're the simple activities. And at the moment, CRAM isn't able to deal with the difficult ones, which require a great deal of deliberation. It's using knowledge to satisfy and provide the information for the generalized action plan, but it doesn't have a huge amount of flexibility. And that's the next phase of the CRAM cognitive architecture, CRAM 2.0, and the next phase of the EASE project. And so the goal is to take CRAM as we have it today and extend it so that it can not just do known objects or known actions with known outcomes, which is what I've been describing, but rather that it could do use a known action to accomplish a new outcome, doing something new with new actions, or maybe it could be using a new action to accomplish something that you already know how to do, but doing it in a different way. Or maybe doing something completely new with a completely new action. So this is what characterizes a cognitive agent, this flexibility. And that's the goal of the next phase of CRAM. So the question arises, well, how are you going to do that? So I'm going to finish off by giving you a whistle-stop tour of a new framework which has been developed as part of a work that was done in the University of Bielefeld. It's called the Situation Model Framework. And it's the mechanism by which we get this flexibility, this context sensitivity, cognitive behavior. So there are 3 different foundational themes. First of all, action is everything in cognition. And so when you think about cognition, don't think thinking, think action. It's all about action. Secondly, when you act, you can scaffold your actions to accomplish more complex actions. So complex behaviors emerge by scaffolding simpler behaviors. And finally, you've got internal attention. And this is a way of prioritizing your control mechanism so that it only does what's feasible and what's necessary in the current context. So they're the if you will, the foundations for the situation model framework. On top of that, then the next foundation stone is this concept of a behavioral episode. Now, this is an important idea in that it captures the causal link between your current state, your object scene, some action, and what the outcome would be. And it's an abstract representation, so it doesn't have the emotion parameter values associated with it. But it is a way of capturing your current state, some action, and what would be the outcome. So it's a way of creating what we call a joint perception, action, representation of the world. So it captures both your spatial and your temporal aspects. And in particular, it captures your causal relationships. Don't know where that is. Oh, I'm going backwards, I'm sorry. Okay, so that's the bedrock, is the behavioral episodes. So this is then the situation model framework. It's got these elements. It's got what we call system 1 for habitual behavior. It's got system 2 for your deliberate behavior. This is for your simple, your easy tasks, and this is for your difficult ones. So I'm going to walk you through these very briefly. So we've got my 2-system approach, my working memory, and my attention, and my cognitive map. So the 2-system approach to thought and action, sorry, beg your pardon. So we've got working memory, attentional control, and we've got our cognitive map. The cognitive map is interesting because it's an extended form of a behavioral episode. Okay, so there are 2 classes of behavior in what is called dual process theory of cognition. We've got our routine, habitual. These are easy activities, or easy tasks, if you will, and they're handled by what's called system 1. The difficult ones are handled through deliberation by system 2. System 1 operates the following way. It has a set of behavioral episodes which match the current context. These are retrieved from memory, and you then look at the behavior of these and you choose one winner. This is called contention scheduling. So one of these behavioral episodes is chosen on the basis of the outcome, and then you execute it, and you've accomplished your action. But because behavioral episodes, as I said, are abstract and they didn't have the parameter values associated with them, you need to fill in these slots at real time, in real time. System 2 then is what takes care of the deliberative processing. And it's got an additional mechanism called working memory. And this allows it to construct new behavioral episodes and predict the outcome using internal simulation. So it's not using ones that you know already, it's creating new ones. It's constructing new behavioral episodes and possibly refining them, and then possibly storing them in memory, in long-term memory. And it's this mechanism that gives the cognitive system its flexibility. So system 1 is focusing on reactive control of action. System 2 is focusing on prospective. That is, it's anticipating the outcome of it by internal simulation. So this is the thing now that sits on top of your behavioral episodes, the 2-system approach. In order to make this work effectively, you need working memory, and you need selective attention. That is, the internal attention is going to provide you with a way of only extracting the information or the knowledge in your memory which is relevant for the current task. And that's your context sensitivity. The working memory is also a mechanism. So let me just pause here. When people think memory, they think passive device, places where you store stuff. Well, don't believe that. Memory is a mechanism. It's a constructive mechanism. It's not a passive device or a passive element in your cognitive architecture. And so working memory in the situation model framework is the place where you set up and create your new behavioral episodes and then predict the outcome covertly by simulating them and possibly then refining them and learning from them and then storing them. So working memory plays a pivotal part in this overall idea, this framework for flexibility. So internal attention and working memory, that's that one. And then finally, you have the cognitive map. So this is an extended form of a behavioral episode. So it's still a perception, action, outcome representation. So therefore, it's capturing these causal links between the current scene and your objects in the scene, the action that you take, and then what will be the outcome. And so it captures that as a network of events. So it's got episodic memory, the autobiographical experience of the robot. It's got procedural memory, encapsulating its skills, and it's got semantic memory, which binds this narrative together, which tells you what's happening, which describes what you're doing, in effect, just like the narrative in a meme. And this is from a recent paper by Vernon. It's a way of organizing knowledge in all domains of behavior in a systematic manner. And so effectively think of a cognitive map, not as a map of how you navigate in the world, but as a map of the causal relationships in the world. So you can see that it's very, very strongly bound up with behavioral episodes, but it's a network of them, if you will. So that then is the situational model framework and how it accomplishes your flexible, context-sensitive cognitive behavior. So to summarize then, it is a way of constructing, simulating, enacting, refining, and assimilating, if they work, your behavioral episodes. So that as you're trying to figure out how to do a task, you are imagining a sequence of possible things that you can do in order to get from your current state to your goal state. In German, this is sometimes referred to as Probehandeln. And the idea is that you are mentally executing an action as a trial to see what would be the outcome, and then you choose the one that gives you the best outcome for the current context. So, and this is what you do as human cognitive agents and what CRAM will be doing as a robot cognitive agent in the future. So it will be enacting out these plans through internal simulation, trying out different combinations of behavioral episodes, which have been extracted from the cognitive map. And so they're captured here in this image where we've got our two system architecture, we've got attention, we've got our capacity limited working memory, we've got our cognitive architecture, and we've got our episodic memory. And all of this together then allows the robot to decide, in order to get the target object, which is being obstructed by something standing in front of it, it has to move it out of the way first. And it does this in its head through internal simulation. So CRAM 2.0, and the next generation of CRAM will, among other things, it will embrace the situation model framework and then give it that flexibility, allowing it to do things that it can't currently do by evaluating the outcome of certain actions in order to achieve the superordinate goal of the particular activity it's carrying out. So back to my pizzas where I started, in a way. So this allows it to do things in a way that it didn't do before, with new actions and with different outcomes. So you can transport with a spoon, you can spread with a spoon, or you can take a lid off something with a spoon. You can transport with a fork or spread with a fork or so on. So all of this is what gives you your flexibility to infer the outcome of an action and the context sensitivity, so that you only look at the things that are relevant for the current task at hand. And that allows us to go from where we are today with CRAM 1.0 and as a cognitive architecture, by integrating the situation model framework into it. You'll be able to do something new with known actions. You'll be able to do something known with new actions. With new actions, and you'll be able to do something new with new actions. And so system one with the situation model framework, which is what we currently can do with CRAM, will be augmented with a system two, which will be able to do the difficult tasks through deliberation by effectively recombining behavioral episodes and simulating the outcome of these and choosing the ones that give you the parameter values that accomplish the task successfully. There are lots of challenges for this, and I've just listed 8 here. How do you do this decomposition and reconstruction and recombination? How do you create hierarchical behavioral episodes? How can we have networks of them? And so on. So lots of interesting research to be done, lots of problems to be solved. and a very, very promising future for the CRAM cognitive architecture and for cognitive robotics in general, focusing on the difficult domain of carrying out everyday activities, because may look simple, but very often they're not. They can be both complex and difficult. And we need a cognitive architecture which allows us to deal with that complexity and to deal with that difficulty successfully. So I just want to acknowledge that this work was funded by the EASE project through the German Research Foundation, the DFG, and it was also funded by the Center for Interdisciplinary Research in Bielefeld University. So thank you very much. And the paper that I was over-ambitious in trying to describe in 3/4 of an hour, my apologies for going through it so quickly, that was made available open access through Project Deal. So thank you very much to everyone.